Good evening, everyone. We are in the week 10 problem solving session of the NPTEL course, Control and Tuning Methods in Switched Mode Power Converters. And week 10 is about boundary control for time optimal recovery. I am Teja Golla, a fifth year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen?
Yes, sir.
Yeah, so till now, whatever we have discussed in the previous weeks, if I summarize. So we have discussed initially about the working of the switch mode power converters. Also, we have discussed about the design, how to design inductance, capacitance, and based on ripple, all the design aspects that we have seen. And then we also seen what are the steady state parameters. So we have also seen the steady state analysis, I would say, in terms of ripple, how to calculate ripple, how to define um, ripple of the inductor current, capacitor, voltage, etc. And then we also seen different architectures, control architectures. I should do control architectures and like voltage mode control, current mode control, all these things we have discussed. And then sir has shown some simulation. So that was also covered, which was again very important. So sir also has covered MATLAB simulations, how to simulate and implement in MATLAB. So whoever has joined it, I was just giving a brief summary of what all we have discussed in the course till now, so that we can connect whatever that was discovered earlier, that was discussed earlier with whatever we are going to discuss today. So week 9, I have covered last week on Saturday, and the video is already uploaded. So today I'm going to cover week 10. Next week there is no session as I'll be out of station, and next week again week 11, and after that week 12 we have. So today I'm going to cover about week 10, which is about the boundary control for time optimal recovery. But before that, I wanted to correlate what all we have discussed and why we have discussed, so that you will get a picture of why we are learning time optimal recovery and how is it very important and useful for us. So as we have discussed in the early weeks, we have discussed about the working of switch mode power converters. We were discussing about different switch mode power converters, and then we have also learned about the designing, how to design inductance, capacitance, and we have also done the steady state analysis in terms of getting the ripple information, duty ratio, steady state duty ratio for both ideal as well as practical converter, and then voltage ripple, etc. All the steady state parameters. Then we have also discussed about control architectures like voltage mode control, current mode control, how to do SR flip flop, comparators, etc. And then we have done MATLAB simulations. Then we have started modeling. So then we have done modeling. So in modeling, we have learned of many things such as we have done circuit averaging technique. So what all did we do? If you remember. We have also done
State space average.
yes, state space averaging. And we have also done averaged switch model. So based on all these things, we got the based on all this, we got the model. So small signal or large signal. So it had both DC plus AC model. Then we have done some analysis, and then what we have done is we got the small signal model. So we got the small signal model. And then using the small signal model, we have learned about the small signal transfer functions. So before I continue, I just want to clarify, have you gone through week 10 lectures so that accordingly I'll deal today's session. So if you have gone through them, it's okay, else I'll just maybe explain certain things. So because I'm doing it ahead, have you gone through week 10 lectures or not yet?
No, sir,
No.
not even started.
Okay. Then I'll just explain what all I'm going to discuss so that it will be clear. Okay. So yeah, small signal transfer functions we got, and then later we went to a very important topic, which is more accurate model as well, because we have seen that there is accuracy limitation when we have considered some approximation. So we have seen that there is some accuracy limitation because of the approximations that we have considered during the derivation of the small signal transfer functions. Then we went to design aspects. So based on again small signal model, assessing small signal model. So here we have done pole zero cancellation, and then for voltage mode control as well as current mode control, and I have taught for buck, and I think Kelvin might have taken few case studies for the boost as well. And then we have seen that there is a bandwidth limitation. So there is a bandwidth limitation in all these cases because of the small signal model, because of the assumptions that we have considered. And then we know that the bandwidth is FSW by 10 usually, and in current mode controls arrays said that we can push till 1/8 of the switching frequency, but like in generic, I can say that the bandwidth we can achieve up to 1/10 of the switching frequency in both voltage mode control and current mode control. Then then the question that we might have asked ourselves is, can we further push the bandwidth, or can we further improve the response? Because the bandwidth is limited, now I cannot further push the bandwidth. So is there any other way to actually improve the response? And the answer is yes. So the answer for so so submission just yeah. So we have asked ourselves one question. Can we further improve the response? Yes. And how are we going to do? Because if we are considering small signal model, then there is some approximation that we are considering in the process, and that will eventually limit the response, because the bandwidth is limited because of the assumption that we have considered. So we cannot make any assumptions, which means we cannot go for small signal model. So in that case, we have to do large signal model. So the overall objective is to go for large signal model. And if we are going for large signal model, one thing that we know is it is no more linear model, because there is a switching action that is going on, and it is non-linear model, right? So till now, is this clear? How we have approached till this point? Why non-linear model is needed? If we are going to small signal model, we need all these things. So we have learned that as well. And we should also learn large signal model, because you could ask, then what is the point of all this? Because if that much performance or that much response is not needed, in most of the cases, it might not be needed, then 90% of the case, in the existing products as well as most majority of the applications, people do small signal model based design and it meets the requirements. So if this is serving the purpose, why to go for large signal model, which is more complicated? So that's why it is equally important to learn the small signal model based controller design. But whenever this bandwidth is not sufficient to meet the requirements of the applications, one such application is the data center application where I am currently working on for my PhD thesis. So in that case, we need to go for large signal model. So large signal model is non-linear. So we had to understand how to deal with the large signal model and how to design. So for that, in the last week, the discussion was about all trajectory. So in the last week, we have discussed about the trajectory as well as phase portrait. Also, we have discussed about the equilibrium points and then also the stability of the system. So this we have covered in week 9 because we need to understand how to deal with such complex systems, or I would say nonlinear systems where there is a switching action and we are not doing any linearizing. We are considering the model as it is, the switching model, and then we are going to deal with it. So we need to understand how to approach designing of such switch systems. So nonlinear, or we could also say switching systems, because it is basically switching system. There is a linear model and it is switching, so that is making it non-linear. So it is a switching system. So how to deal with it? We need to do from trajectory point. So what is trajectory? So for that, we need to understand the phase portrait, which is the like the motion of the system with the time, and then we are dealing with only state variables. So we are drawing the plot of x1 and x2. So basically the time is not there in the plot, but when we are drawing the trajectory, it is with respect to time. So with time, how is it moving, whether it is moving from the equilibrium point. So we also have to learn what is equilibrium point, what are eigenvalues and eigenvectors. Based on that, we have decided whether the trajectory is going towards the equilibrium point or whether it is going away from the equilibrium point, which is very much important. So we also had to discuss regarding the stability. So for this stability, we have also discussed about the eigenvalues. And then we have also discussed about eigenvectors. So why? Because eigenvalues decides the stability of the system, which we have discussed last week. So if you have not gone through, you can also go through that. I have uploaded the video, so please go through that. And eigenvectors decides the trajectory, how it is going towards or away from the equilibrium point. So now that we have understood how to deal with these nonlinear models, how we can approach that, this week we are going to learn about sliding mode control. So in this week, we are going to discuss about the sliding mode control, which is again trajectory based, which we have learned last week. And we'll also learn another important topic, which is the time optimal control. So we are going to discuss about the sliding mode control, which is trajectory based, and time optimal control is also based on trajectory. So we'll see how to get the details regarding the waveform current, how inductor current and output voltage responds during this time optimal control. So is this clear till this point?
Yes, sir. Sir, that large signal model we will mostly be taking when the like uh, perturbations are large. Under that circumstance only, or any other cases where we need to take large signal rather than small signal, where small signal will not give accurate results.
Yes, yes. So one good thing that you have pointed out is whenever we are considering large perturbations, small signal model will not be applicable. So in that case, we have to consider large signal model. In addition, when our requirements are higher, like the transient requirements for my application are higher, and then the small signal model is not able to reach that fast transient response because of the bandwidth limitation, then we have to go for large signal model.
Okay, fine, sir.
So I'll just give some brief introduction. Sorry. So I'll just give some brief introduction about what this sliding mode control is about. So what happens is yeah. So if we draw the so if we consider any surface like this, which is sigma equals to 0, and say this is my x1 and this is my x2. So now because of uh, the switching, we have two regions. One is on state and one is off state. So the on state dynamics are different and the off state dynamics are different. So say this is our equilibrium point. This point is our equilibrium point, and we are starting from somewhere. Say we are starting from this point, and my objective is to switch between q equals to 1 as well as q equals to 0, and then based on this switching, I need to go from this initial point to the final equilibrium point. So in the case of time optimal control, so time optimal control basically means single switching. So one on time plus one off time. So we have to find this sigma equals to 0 surface so that my converter will go in this way. So during on, say if it is going like this, and during off, it should reach this point. So this is my objective in the time optimal control, where it hits this line during the on state, q equals to 1. So this is q equals to 1, and then this is q equals to 0 in the case of time optimal control. Whereas in the case of sliding mode control, what happens is this trajectory will hit this surface, and then it will move along the surface towards the equilibrium point. So this is the direction and this is the direction. So it is moving along the sliding mode control. So I can say that this side of the region is q equals to 1 and this side of the region is q equals to 0. So when q equals to 1, it is hitting and going the other side of the line, and when it is off, then it is coming to this side of the region, and it is actually happening infinitely small, so that it is it's as if it is sliding on the surface. So if I further go into like small details, we know that the switching is happening. So q belongs to 0 and 1, and our state space model is a function of q. So we'll have two equilibrium points. Xc belongs to Xc plus as well as Xc minus. Right. So we have one equilibrium point corresponding to 0 as well as one equilibrium corresponding to 1. And then based on this, I can also get the function. Say if x is belonging to f1 as well as f2, I will have a function. One is f plus as well as f minus. So this is the advantage that I am getting because of this switching system, because I have two equilibrium points, and then I have two this f vectors as well as I have q equals to 1 as well as q equals to 0. So it is trying to oscillate between this region as well as that region. Now I have to take the advantage of that switching pattern, and I have to make sure that it will pass along this sigma equals to 0. And we have discussed that how to make a like trajectory flow along the line. So in the last week, we have seen if the trajectory is starting on the eigenvector, then yeah, on the eigenvector, then it will flow along the eigenvector. And that is for linear system because it doesn't have multiple equilibrium points. But if we are considering a switching system, it has two equilibrium points, right? So we can say that xc plus is on this side and say xc minus is on this side, right? So say one is stable and one is unstable. And now what happens one during q equals to 1, it will try to go to xc plus and then that will push back to xc minus. So there will be this switching operation and we have to use that switching operation and then make sure that the trajectory is flowing along the surface, which is this sigma equals to 0. And as you know, now sigma is dependent on x1 and x2. So I can consider k1 x1 plus x2 is equals to 0. Because it's a two-dimensional, my sigma will be a single dimension and it's a function of k1 and sorry, x1 and x2 with again k1. So the slope is negative, which is minus k1. And then I'm getting this kind of operation. But there is one issue in this operation, which is say q equals to 1 is my on time, q equals to 0 is my off time. So for certain duration, there will be on state trajectory, there will be certain duration for which off state trajectory is there. But when the trajectory is flowing along on the direction or on the switching surface, this sigma, then q equals to 1 is also 0, q equals to 0 is also 0. So it is infinitely small value that it is turning on and off very quickly. But this kind of switching action means the switching frequency is tending to infinite. So what happens? That kind of practical implementation is not possible. So this is practically not possible. To achieve because the switching frequency is too high. So in such case, what we do is we'll consider a hysteresis band. Right. So we'll consider such hysteresis band. And I'll use a different color for the hysteresis band. Okay. So now this is my sigma equal to k1 x1 plus x2 equals to 0. And the top one is having some positive offset. Say sigma 1 equal to k1 x1 plus x2 plus c1 equals to 0. And then this bottom one is sigma 2 equals to k1 x1 plus x2 plus c2 equals to 0. So now what we are going to do is say my initial condition is here. Previously it is hitting sigma and then it is turning on and off quickly. Now we have two surfaces. So maybe I should do this. So this one. So the inside sigma is not there actually. Instead of this sigma, we are having two such surfaces with some hysteresis. So now what happens? It will hit the top one during on state and then once it hits, it will turn off. And then there will be off state. Once this hits the below sigma, then will turn on. And once again, this hits will turn off. And then again, it hits, turn on, and then it reaches the middle point. So now this hysteresis, which is C1 minus C2, so the hysteresis band is C1 minus C2. Mod, or we know that C1 is higher, so C1 minus C2. This decides the switching frequency. So now we are letting it turn on for some time as well as turn off for some time. So if we decide the switching law, like what is happening whenever the trajectory is trying to go above the sigma 1, then we are turning it off, and whenever it is trying to come below the sigma 2, we are trying to turning it on. So it is like a hysteresis control. We are deciding the band that will decide the switching frequency, and because this is my equilibrium point, finally my objective is to make sure that it will reach over here. So now we are shaping the trajectory. Previously, also we have shaped, but it was going along the sliding surface, which is not practically possible because of the infinite switching frequency. Whereas in this case, I have put a hysteresis so that I'll have finite switching frequency. I can play with the hysteresis depending upon how much switching frequency I want the converter to operate at. Accordingly, I will decide sigma 1 and sigma 2 because it's basically the constants. And then I will make sure that it is still sliding across the sliding surface to reach the equilibrium point. So this is my final equilibrium point. So is that clear? Like till now, if you have any doubts, you can ask, else I'll try to explain again. But I'll continue the discussion. The discussion is not over yet.
Sir, so basically earlier the like oscillation, so to speak, along that pink line that would be infinitesimally small, like in
Yes,
the
yes.
sliding mode control.
Yes, yes.
But here we are assuming some sort of
Hysteresis.
a gap. Hysteresis
Yes.
we are considering
Yes.
to like between those two values it will fluctuate.
Yes, yes.
So any issues between this like sliding mode control mode is more like
This is also sliding mode control, but with hysteresis. This is
okay.
without hysteresis.
Okay. So with
Because this is
hysteresis, is
also
it less accurate? Like because there is a small gap that is
yes,
taken
yes. It's
to reach
not
the
like
final state.
accuracy. It's like only practical implementation. So in simulation, you can implement both. Sir has shown both, but practically you cannot turn on and off any switch with this infinitely small on time and off time because it takes some time for it to turn on. So I cannot do this, but I can keep some hysteresis band, although I have made it look like it is big, but it need not be big. I have just expanded so that we can see what is inside. I will fix a switching frequency, say 100 kilohertz. Accordingly, I'll have to see how much is my C1 and C2. Then I'll fix this hysteresis band, and then I'll have to choose sigma based on the design. I have to find K1, K2 that sir has not yet like explained in this week, which will come in the next week. Once we decide sigma 1, sigma 2 and the gates, then my trajectory will enter this band and then it will slide across like around that band and then reach the equilibrium point. But if I make it small, it will look something like this. So if I now it will enter and then it will go like this. So basically it's the same thing as the previous case, but here it is very small. Here we are keeping finite value so that it can be practically implemented. But both are the same, that just the practical implementation.
Okay, got it, sir.
So basically, the green corresponds to Q equals to 1, and then the black corresponds to Q equals to 0. Right. So basically, we are calculating sigma, and if the sigma value or sigma 1, say, you know that this side of the region, sigma 1 is positive, and this side of the region, sigma 2 is negative, right? because below this sigma 2, the value of the sigma 2 will be negative. On the sigma 2, it is 0. Above that, sigma 2 is positive. Similarly, sigma 1 is positive above it. On the line, it is 0, and sigma 1 is negative below this line. Now, my control law, so this is called control law. My control law is such a way that Q is 1 if sigma 1 is positive and 0 if sigma 2 is negative. So in the MATLAB simulation, I will be calculating sigma 1 and sigma 2 based on my states. So this is my x1 and this is my x2, right? Say my x1 is capacitor voltage, and then this is a inductor current and or capacitor currents are as considered, but assume that it is related to inductor current. I know inductor current, I know capacitor voltage, so I'll calculate sigma 1, and then which is k1 into vc plus il plus c1 is which is the constant that we have fixed, as well as sigma 2 I can find out. So now I know the trajectory, so I know the instantaneous values of x1 and x2. So I'll substitute x1 and x2 and check in the sigma 1. If sigma 1 is coming positive, then I will turn it off, right? So if sigma 1 is positive, then I should turn off. So, sorry. So if it is going above sigma 1, then I'll turn off. And if it is going below sigma 2, then I'll turn on. So that the trajectory is within this region, and over time it will reach the equilibrium point and it will stay there. Is that clear? So this is how we are deciding whether the trajectory is turned on or off based on the hysteresis. Is that clear? The control law. Hello.
Sir, in PI controller and in that we
Yes.
have some reference current and reference voltage. Here,
Yes.
is it like something like that? Because
Yes,
we are
so
not mentioning any reference.
yes. So here we are not having reference. So here the decision is taken by calculating the sigma 1 and sigma 2. So my trajectory is coming, right? So at every instant I have to calculate whether the trajectory is going above sigma 1. So if it is going above sigma 1, then sigma 1 value is positive. So sigma 1 of x1 comma x2 will be positive. So based on the trajectory, I am calculating my sigma 1 of x1 comma x2. If it is positive, then it means the trajectory has gone just outside the just above sigma 1. Then I know that I have to turn off the my converter. Then once I turn off, it will come back again. And then once it hits sigma 2, and if it is going below, then it means sigma 2 of x1 comma x2 is negative, which means I have to turn on. And then I'll turn on, and whenever again it hits this. So here we don't have current reference as such. So now our reference is a line which is a function of both IL as well as VC. Previously we had inductor current and inductor current reference. So whenever it is hitting the inductor current, we are turning off. And then because it is fixed frequency, after certain time period, we are turning it on. But here it is not fixed frequency anymore. It is like a variable frequency because it is hysteresis control. So now we have assumed that we have peak current as well as valley current. So I can correlate it something like this. I have peak current and valley current. And then this is my inductor current. So now from here, I can get my on term. So this is my gate pulse. So in the similar way, instead of inductor current, I have trajectory. And instead of current reference, I have two surfaces, switching surfaces. So except that everything is just the same. So imagine this as peak current reference, this is valley current reference, and this is my inductor current. Now peak current reference is the upper switching surface, valley current is the lower switching surface, inductor current is the trajectory. So basically here we are shaping the trajectory. So this is neither inductor current nor voltage, but it's the information of both. So that's why we had to learn trajectory in the last week. And then once we are clear with the trajectory, which is a trajectory is a information of state variables and how they are traveling with time. So this is the time information. Although the time information is not there on the plane, with time we are drawing x1 and x2 with time. How they are traversing or how they are changing with time. So that's what we have drawn over here. Is that clear?
Yes, sir. Yes.
So there is less than a minute. Once this meeting ends, kindly join back. So I have made few questions, thinking that I'll ask you to do, but because you have not gone through the lectures, what I'll be doing is I'll solve the problems and I'll explain so that now things will be more clear. But there are certain things that sir has discussed in the lecture. I'll teach certain things, but I may not get time to teach everything. There I'll ask you to go through SARS lectures. That part you go through SARS lectures and then you can refer back. But I'll try to teach most of the things because you have not gone through the lecture videos. So is that clear? If this meeting ends, kindly join back. Once we come back, we'll start solving the problems. Is that clear?
Yes, sir.
So yeah, okay. So the first question is about boundary points and what are the boundary points and how to draw the trajectory for each case and in which of the cases uh, there is chattering behavior and what is the reaching condition. So first I'll show that there are three cases for boundary points. What are those? I'll explain. So there are three boundary points. One is the refractive point. And one is the reflective point. One is the rejective point. And all are based on the trajectory only. So these are the three boundary points that sir has explained. Okay, so now what is refractive point? What is reflective point? What is rejective point? So we have considered the switching surface. So for three cases, we have considered three switching surfaces. So all are sigma equals to 0, sigma equals to 0, sigma equals to 0. So first thing is the refractive point. Okay. So what happens in this point is it will hit like this. So one side it will try to push, other side it will try to go away. And then in this case, what happens? It will hit like this. Now again there will be on time, and then now again there will be off time, and then in this way it reaches the point, right? In the case of reflective point, this side also it will be inside, this side also it will be inside. So from both the sides, the trajectory wants to come this side. If you see in this case, if we are starting from this side and if we are hitting the other side, the direction is away from the line. So on one side it is towards the line, on the other side it is away from the line. So one side it is going towards the line, other side it is going away from the line, and again towards the line, away from the line. But if we have to design the controller in such a way that it will converge, right? But there can be a situation where it is diverging also. Maybe I'll show that, then things make more clear. So in this case, there can be a scenario where it is diverging. So So this can also happen, right? So either it can converge or it can diverge as well. So this is stable and this is not stable. It is moving away from the equilibrium point. It is moving towards the equilibrium point. Because one side it is trying to come towards the point, line, one side it is going away. So the trajectories look something like this. Whereas in this case, both are trying to come towards the line. So if we are doing that, so say now we are starting from here and then we have just crossed. Again, it will has to come towards this again. So it will go on the line, right? As discussed. So it will reach the equilibrium point finally, but it will have infinite switching. So this is called reflective point. This is refractive, this is reflective. Because both the sides, it is trying to push towards the line. Whereas in this case, it is coming towards the line on one side and away from the line on the other side. So that's why it's called refractive, as if it is getting refracted. But this is on both sides, it is trying to push towards the line. So it will travel on the line towards the final equilibrium point. Say this is my equilibrium point, it will try. But whereas in this case, it is rejective. So both will try to push the trajectory away from the point. So say I have something like this, it will try to push like this, or it will try to push like that. Say this is my equilibrium point, right? Final equilibrium point. It will never be able to reach that. So we don't want this. This is called rejective. This is rejective point. Because this side it is trying to push the trajectory away from the line, same it is happening on the other side. With this, will never converge to the equilibrium point. Whereas in this case, it will have infinite switching frequency as discussed. Whereas in this case, it will take finite switching frequency because this is on, this is off, this is on, this is off, this is on, this is off. So there is some finite non-zero duration for on time as well as off time, and it will finally reach equilibrium point if it is stable. Else it can also move away from the equilibrium point. So this is a refractive point. So these are the boundary points, and this is how the trajectory will look like. Now this infinite switching frequency is also called as chattering. So this kind of phenomenon is called chattering. So the reflective region exhibits chattering behavior. So this is called chattering behavior. Is this clear?
Yes, sir.
And I have given this question reaching condition because it takes time to understand what is reaching condition, but I am not considered in today's session because it will take time. Instead, we can spend time on solving other problems. So for this, the sigma sigma dot should be less than 0. I am not teaching this, but I'll say that kindly go through sir's lectures because it takes time to explain this. Instead, we can spend time on other problems where I can actually teach because this part will take more time. Instead, I could spend on multiple topics and cover multiple topics. So kindly refer sir's lectures for this. So reaching condition is in which case it will reach equilibrium point. So this is basically about equilibrium point. So sigma sigma dot should be less than 0. Then only it will reach the equilibrium point, else it will not reach. So only this part you have to go through source. Sorry, not source condition. Source lecture. Just you have to go through search lectures. I think it is in the last but one lecture of this week. So you go through last but one lecture. I think 1 hour is there. In that, sir has explained reaching condition. Only this part I may not get time to cover in today's session, but other aspects I teach. So is this clear? The first problem. what are different trajectory points and how the trajectory looks like, and this is chattering behavior, and it has infinite switching frequency. This has finite switching frequency. Clear?
Yes, sir.
So only this part. Sorry for this because I will not get time. Next question is about switching surface, which we know as sigma. So sigma is a function of state variables, right? So if we are considering an input with u, so input is 1. So the number of switching surfaces are equal to the number of inputs. So number of switching surfaces equal to number of inputs. If we have one input, then we'll have one switching surface. Else we'll have more switching surface. So considering this sir has explained, because we have say single input, then we'll get only one surface related to that input. But if the input changes, then the line, whatever, that also will change. So depending upon the inputs, we'll get new switching surface. But here I have given one input u, so that we'll have one switching surface. So for a second order system means we'll have x1 and x2, right? Right? So my sigma is a function of x1 and x2. So I can write k1 into x1 plus x2 equals to 0. So now, what is the dimension of this sigma? Is it a line or plane or what? Anyone? K1 x1 plus x2. Is it a line or is it a plane or what? What is it?
Straight line.
Straight line. Very good. So this is a straight line. So if we draw, because it's a 2-dimension, we have something like this, x1 and x2. This is x1, x2. So we have a line passing through origin. But if we consider hysteresis, then it is slightly above origin and below origin. But we are now not discussing about the hysteresis part, which is practical implementation. So we are only discussing about the ideal cases. So this is sigma equals to 0, which is k1 x1 plus x2. You know that k1 x1 plus x2 equals to 0 is a straight line passing through origin with a slope minus k1. So the line will look like this. So the switching surface is a line, straight line. It's a 2-dimensional straight line. Now, sorry, single dimensional, not 2-dimensional. Single dimensional line. Line is one dimension. So third order system. Now we are going for a third order system. So no doubts, right? In the first part. Anyone having doubts, or I hope it's clear, right? First part. Okay. So now because it's a third order system, the sigma has to be a function of x1, x2, and x3. So this is a generic expression, which is k1 x1 plus k2 x2 plus x3 equals to 0. So now is it a line or is it a plane or what is it? Sigma? Anyone?
Plane,
Line, right? Or plane?
plane, plane.
Plane. Yes. So this is a plane. Dependent some issues. Just give me a minute. Try to resolve.
Sir, is it because that magnet symbol that is turned on?
I think it is automatically turning on. I think it's always on. I don't know whether it's some connectivity issue with the pen or I'm not sure exactly. So, sorry for that. This window actually, so here we have another one, here we have another one. So basically it's a three-dimensional. We have x1, x2, x3, and say we have a plane passing through origin. So it's a plane in 3D and it is passing through origin. So the plane is a 2D. So this is now this sigma equals to 0 is k1 x1 plus k2 x2 plus x3 equals to 0. It's a two-dimensional plane in 3D space. Now if we increase the dimension, then we'll have fourth order system, and then the switching surface dimension will be again one less than that. So it's a three-dimensional. So we have f of x1, x2, x3, x4, and from this we get sigma is k1 x1 plus k2 x2 plus k3 x3 plus x4 is equals to 0. Now this becomes a surface. It's not a plane, it's a surface. It's a three-dimensional surface. So now we can only draw sigma, but not the system because it's a fourth dimensional and that we cannot draw. We can only imagine. So you can consider like fourth order system is there, which we cannot imagine. But the sigma itself is a three-dimensional. So the sigma is three-dimensional. So the trajectory is moving on the 3D, but considering there are higher dimensions, which we cannot actually visualize because we are 3D bodies. So the sigma it's a 3D surface. But if the system is fifth order, then sigma will have fourth dimension. Sigma will be 4D. So the dimension of sigma will be one less than the dimension of the system. Say if sigma is mth order, and then f or x is, say if sigma is m cross 1, and then say x is n cross 1, then we know that m is equal to n minus 1. So this is one order less than that, and depending upon the order of this, the order of this is decided, and we can get the information about that. Is that clear?
Yes, sir.
Okay. So now we'll solve another problem. So now this is first part you will be able to solve. Second part I'll teach. So can you find the equilibrium points? So U is my input. So I have here U is switching between say 8 and minus 8. My input is switching between 8 and minus 8. Like input can change between V in and 0, right? Q into V in. V in is changing from Q into V in is changing from V in and 0. Similarly, I have an external input U, which is switching between 8 and minus 8. So can you find the equilibrium points of this?
X dot equal to 0, we can equate.
Yes, very good. So for calculating the equilibrium points, we'll have to do x1 dot equals to 0 and x2 dot equals to 0. And then we have to find for solve for x1 and x2. So can you solve and then let me know what are the values of x1 and x2?
4 comma 0 and minus 4 comma 0.
Others are also getting the same answer? Or maybe I'll just wait for 1 more minute. So, is that Arun who has answered? Are you getting 4 comma 0 and minus 4 comma 0, right?
Yes, sir. I got x2 equal to 0. For
Yes.
u equal to 8. From the second equation, I got minus 2x1 equal to 8. So x1
Yes.
is 4, like that.
Yes. So if we equate x1 dot equals to 0, we'll directly get x2 equals to 0. And then once x2 is 0, from the second equation, I'll get minus 2x1 minus u is equals to 0. So I'll get minus 2x1 is equals to u, or I can say x1 is minus u by 2. But based on that, I'll get x1 is plus or minus 4. So now I have two equilibrium points. So I can say my x1 comma x2 has two values. If u is positive, then I am getting minus 4 comma 0, else I am getting 4 comma 0. So this is when u is 8 and this is when u is equal to minus 1. So this is how we calculate the equilibrium points. So once we calculate the equilibrium points, then I am asking the range of C for which the sliding surface is stable. So sliding surface, because now the trajectory is moving on the sliding surface, right? So here we have a two-dimensional system. So this part I'll explain because this is covered in the lecture. So we have sliding surface passing through origin with dimension C1x plus C. So this is my sigma equals to C1 x1 plus C2 equals to 0. And this is x1, this is x2. After certain time, the trajectory started moving on the switching surface. So the possibilities, either it can travel like this, or if we consider the line something like this, we can also say the trajectory can move away from the equilibrium point, right? So this is my equilibrium point, say minus 4 comma 0 or 4 comma 0, any one of them. So either the trajectory can come towards the equilibrium point on the sliding surface, or it can go away from the equilibrium point on the switching surface. Do you agree? Because there are two possibilities. Till now we have only discussed that it is moving towards it, considering it is stable, but it can also move away, right? Do you agree?
Yes, sir.
So now we have to see how the trajectory is going for this given condition. So what we basically do is we'll have to find the trajectory for the given given system. We will have to calculate x1 and x2 function and see whether it is with time reaching this point or whether it is not. So for that, what we'll do is we know that the system, these are the system dynamics, right? So x1 dot is given. So my x1 dot is equals to x2, and x2 dot is nothing but minus 2x1 plus 4x2 minus u, minus 2x1 plus 4x2 minus u. So now the system has to satisfy this, and if it is traveling along the switching surface, then it should also has to satisfy C1 x1 plus, not C2, it should be x2. Sorry, this is not C2 plus x2. So C1 x1 plus x2 equals to 0. So it is satisfying all these three cases. But I may not need all three. What I do is I substitute this in C1 x1 plus x2 equals to 0. So now this will give me C1 x1 plus x1 dot equals to 0, or I can say x1 dot is equal to minus C1 into x1. So can you tell me what is the solution for this? X1 dot equal to minus C1 x1. We have discussed in yesterday. So if you have not joined, so we can write this as dx1 by dt is equals to minus C1 into x1. So I'll bring x1 here. So 1 by x1 dx1 is minus C1 into dt integral. So I'm doing from 0 to t. 0 I'm calling x1 naught, and then it is reaching x1. So now I will get ln of x1 by x1 0, which is the initial condition, is minus C1 into t. So from this I will get my x1 is nothing but x1 0 into e to the power minus C1 t. So this is the dynamics of x1 along the sliding surface. Now I know that if x1 is tending to 0, then it is coming towards the equilibrium point. If x1 is increasing, then it is going like this. So if I redraw this, so if I redraw this and then say my initial condition is like this, so if it is going in this direction, then C1 should be positive, right? Then C1 is greater than 0. But if it is going in this direction, it means C1 is less than 0. Because my solution says x1 equals to x1 0 into e to the power minus C1 t. So it will tend to 0 only when C1 is positive. So the system is stable if C1 is positive. If C1 is positive, then x1 will die down and it will reach 0, 0. Else it will keep on increasing and then it will go away from the equilibrium point if C1 is negative. So there are two cases that can be possible along the sliding surface, and we have considered the dynamics of the system and the dynamics of the switching surface, and we have converted into one variable. Now, if we know x1, we can substitute x1 in this and solve for x2. But we already know that in one case it is stable, which we can get from this. But if we want to find the information of x2, then we have to solve for the other equation depending upon if u is 8 or u is minus 8. So, but this is the overall picture. Is this clear?
Yes, sir.
So I have maybe many things are not clear because we have not gone through the videos, but I tried to teach as much as possible. But if I think you still might have some confusion, you will anyways go through such lecture, and I highly recommend it. But till now we have discussed about the first thing, which is the sliding mode control, where it is sliding across the surface and it is switching multiple times to reach the equilibrium point, and this is the trajectory based approach. Similarly, time optimal control is there, which is also of course trajectory based approach, but we are saying time optimal because it should take optimal time to reach the new operating point. Okay, so we have discussed only about sliding mode control, sorry. So now we are going to discuss about another topic, which is the time optimal control. So I'll give a brief introduction of time optimal control based on the trajectory. But once you get the idea, then we'll solve mathematics, and then we'll see what are the inductor current and capacitor voltages and how they're changing. So first I'm considering load transient. So this is my IL and this is my capacitor voltage VC. So load transient. So initially say IL1 and capacitor voltage is what? Output voltage. Output voltage is always regulated. So it will lie on the same vertical. It will lie on the same vertical line, right? Agree? All of you? So initially, you can say that my initial equilibrium point is this, which is IL1 comma VC1. Now my load current has increased, but my output voltage should be regulated at the same value, right? It cannot vary because my controller must ensure that the voltage is regulated. I am reaching this point, which is IL2 comma VC2. Is that clear? This part? If you have any queries, you will ask. You should ask, then I'll explain this. It will be difficult as we start solving that. Is this clear? Why they should lie on the same point? Navin says yes. I hope for others also it is clear. Now, with all the knowledge that we have learned, we know that trajectory has on trajectory, off trajectory, and there is a surface signal. What we are doing is we want to hit the surface during on trajectory, and after the off trajectory, we want to reach to this new operating point. So let us assume that sigma is somewhere here. Okay, so this is sigma. Now what we are doing is during on state trajectory is hitting here, and during off state trajectory. So this is my q equals to 1 or on state trajectory, and this is my q equals to 0 or off state trajectory. Clear? This is what we are trying to achieve, optimal control, because single switching state. So it has single switching, which means one on duration plus one off duration. So we have the sigma over here. We are trying to hit it during on state, and then we want to reach the new operating point at the end of the off state. And now you know that this is what refractive, right? If you go back, this is our refractive point. If it is reflective, then it is sliding mode control. If it is refractive, then we are getting what we are actually hoping for. So this is refractive point. This not the highlight, this is refractive. Is that clear?
Sir, that particular shape, is it because when Q equal to 1, inductor current increases and the capacitor voltage decreases? Is it because that shape?
Yes, very good, very good. Very nice point that you have raised. So yeah, thanks for raising this point. Whenever there is load transient, you know that there is a dip in the output voltage because of the load current, and while the inductor current is rising. And after that dip, it tries to come back to the same. Actually, this is not VC2. So this is same as VC1. So this is VC1. So it tries to come back to the same voltage, but in new like new inductor current. And this is like a dip. So now that you have raised, I'll consider time domain waveform also. So say I want to consider the inductor current something like this. and then there is low transient, and then it will come back. And then so this is the optimal trajectory. So one on state, one off state, and it will reach. So that is my objective. So now I have to draw the voltage. Or first I'll draw the capacitor current. So this is my IL, as you know. Now I will draw IC. IC is basically nothing but IL minus I naught, right? So if I draw, I'll get something like this because average value should be 0. And you know that whenever there is low transient, initially the capacitor will supply the current, right? You know this, right? Capacitor will supply the current. So this is my capacitor current. So this is my capacitor current. Is that clear? Because this is my delta I naught. Initially, again, delta I naught is nothing but IL2 minus IL1. So I am calling this average is IL1. This average is IL2. And then the change is delta I naught. So initially that delta I naught will be supplied by the capacitor, and then capacitor will try to charge and then reach like this. If we draw the capacitor voltage as well. Okay. This. So there time is less than a minute if this meeting ends. Kindly join that. And then until this, there will be undershoot. And then once the capacitor current is positive, then it will come back. So this is my V0. And this is delta V undershoot. Is this clear? Or maybe I'll explain once again the meeting ends. We'll join back and then I'll explain again. Do you have any doubts? If this meeting ends, kindly join back. Any doubts until this point? Can you see my screen?
Yes, sir.
Yes. So if we correlate, this point IL1BC is before the transient. So this is IL1 and this is at VC, right? So this is the average value is at VC. Okay. And then once there is a transient, IL1 is trying to increase to hit some peak, which is this peak. This peak is same as that peak. And during that peak, in between the voltage is falling. So once the voltage is falling, And after this, the inductor current is trying to come back, and then voltage is also increasing. So inductor is coming back, and then voltage is also increasing. So the after the steady state, IL is at IL2, IL is at IL2, VC is at same. So it has come back to VC1, and this is my delta V undershoot. So now this is the time optimal where it is turning on and then off and then coming back. And this is the capacitor diagram. And then this is the output voltage which has undershoot. And once IC is positive, then it will start increase. As long as IC is negative, capacitor will discharge. So is this clear? Just to correlate, this peak point is this peak point, which we are going to calculate. So now in this time optimal trajectory, we would like to find how much is the settling time and how much is this I peak as well as how much is the delta V undershoot. So we are going to calculate and then understand the thing. So this is my I peak. And then this can be considered as T1, this as T2, and this as T3. Again, we are neglecting the ripple. So till this point, is this clear? Like if you have any doubts, you can ask. Else, once we go to the math, then it will be difficult for you to understand. So if you have any queries now, you can ask.
Clear, sir.
Clear, right? Okay. Now let me copy only this IC part. And using this IC, now we are going to calculate certain things. Okay. So you know capacitor charge balance. So again, we are making one assumption. I will highlight it here. Ripple is small. So now what we are doing is we are going to calculate this area. And then we are also going to calculate this area. And then according to charge balance, both should be same. So Q1 should be equal to Q2. Okay. And we also know that this slope is M1. This slope is M1. And then this slope is M2. So my objective is to find I peak as well as T1, T2, and T3. So once I find that, I know I peak. If I know T1, T2, T3, then I'll sum it to get the settling time, which is TS. Okay, so now I'm going to ask you, can you tell T1 in terms of delta I naught as well as M1? Again, ripple is small, so ripple you can neglect, so you can consider it to be triangle. So I need T1 in terms of delta I naught as well as M1.
M1 equal to delta I naught by T1.
Very good. So M1 is equals to delta I naught by T1. So from there I can get T1 is delta I naught by M1, right? T1 is delta I naught by M1. Agree?
Yes, sir.
Now can you tell T2 as well as T3 in terms of I peak M1 and M2?
I peak by M1 is T2 and
Very
I
good.
peak by M2 is T3.
Very good. So I peak by M1 is T2 and I peak by M2 is T3. Okay, very good. Now what we are going to do is, we know charge balance because the capacitor current should follow charge balance so that the effective charge is 0, which means Q1 and Q2 should be equal. So now we'll apply charge balance. Which means Q1 is equals to Q2. So Q1 is area under the curve. So can you calculate what is Q1?
Area of that triangle half BH.
Yes, half BH. So what will be the value?
1 by 2 into delta I0 into T1.
Yes, very good. So we'll do half into delta I naught into T1. Okay. Now, what about Q2?
Uh, 1 by 2 into I peak into T2 plus 1 by 2 into I peak into T3.
Yes, very good. So I can write half base into I. So if I combine the base, it will be I peak into T2 plus T3. So now what we'll be doing is we have say this is equation 1, equation 2. We'll substitute T1, T2, T3 in equation 2. So please try to solve along with me. So what will be on LHS? First of all, half and half I will cancel. Half and half is cancelled. So what is left on my LHS?
Delta I naught square by M1 equal to.
Yes, very good. So delta I naught square by M is equal to I peak into, again if I take I peak common, I'll get 1 by M1 plus 1 by M2. So if I take denominator common, this is what I'll be getting. Agree? Simplification, do you agree?
Yes, sir.
Now M1 and M2 M1 and M1 also will get cancelled. So now if I calculate IP square is nothing but delta I naught square into M2 by M1 plus M2. So now I can calculate IP. IP is nothing but delta I naught into square root of M2 by M1 plus M2. So this is my IP. Agree?
Yes, sir.
Others also, I hope you don't have any doubts till this point. So just to quickly summarize, this is my capacitor current. So from the slopes and these values, we know T1, T2, T3 in terms of I naught, delta I naught, I peak, M1 and M2. Once we get those, using charge balance equation, we know uh, the area under this and area under this should be equal magnitude. So we are equating the magnitude and substituting everything. Now I got I peak is delta I naught into M2 by M1 plus M2. So now let us consider a buck converter because uh, I will be mainly discussing about buck converter. So if we consider buck converter, what is M1 and M2? Anyone? What is M1 and M2 in buck converter? Riddhi is saying Vi minus V naught, very good. And M2, V naught by L, very good. So in case of buck converter, we will get M1 is V input minus V naught by L and M2 is V naught by L. So now, can you simplify and tell me what will be IP? So after substituting,
Sir, are we taking the slopes of capacitor current and inductor current as same?
yes, slopes will be same, right? Because IC is IL minus I naught and I naught is constant. We are considering constant. So the slopes are same, yes.
So only for buck converter we are doing this.
Yes, only for buck converter. So Riddhi is saying delta I naught into square root of D. Very good. Others also please calculate. Substitute M1 and M2 and let me know what you are getting. So have you calculated IP?
Delta I naught into root of V naught by V.
Yes, very good. So IP is delta I naught into square root of V naught by V, and we know for buck converter, this is duty ratio. So IP is nothing but delta I naught into root D. Yes. So we got I peak. Basically, our objective was to calculate I peak, and then we have to calculate TS. So now we'll calculate TS. So first, for calculating TS, what we'll do is we'll write T1 plus T2 plus T3. So this is my delta I. Then I got I peak is I naught into OT. First, let us solve for T2 plus T3, then we'll come back to T1. So T2 plus T3 is nothing but delta I naught into root D into M1 plus M2 by M1 M2, right? So now what is M1 plus M2? V in by L, right? M1 plus M2.
Yes, sir.
And M1 M2 is V in minus V0 into V0 by L square. So if we simplify this, we'll get, or let M1 be M1 and we'll only do M1 plus M2 by M2. So it will be opposite of this. So I'll take M1 outside. So I'll get delta I naught by M1 into square root of D into V in by V naught, which is 1 by D. So I'll get delta I naught by M1 into 1 by root D. Agree? I have taken M1 aside because T1 also has M1, so that it will make my life simpler for the calculation. So I have only basically calculated M1 plus M2 by M2. M1 plus M2 is V in by L, M2 is V naught by L. So L will get cancelled, it will become V in by V naught. Is that clear?
Yes, sir.
Okay. So now let us calculate the settling time TS, which is T1 plus T2 plus T3. T1 is delta I naught by M1, and this is delta I naught by M1 into 1 by root D. So now if we take delta I naught by M1, we'll get 1 plus root D by root D. Now let us calculate what is M1. M1 is V in minus V0 by L. And say V naught is constant. If I take V naught constant, I will get V in by V naught minus 1 by L. And V in by V naught is what? 1 by D, right? So I'll get 1 by D minus 1. So if I simplify, I'll get V naught into 1 minus D by L into duty ratio. Agree?
Yes, sir.
Okay. Now let me calculate it. TS is delta I naught by M1 is V naught into 1 minus D into D into L. I'll bring here into 1 plus root D by root D. So now if I make cancellation, this will be cancelled with 1 minus root D, and this will be cancelled with root D. So now TS is equals to L into delta I naught by V naught into square root of D by 1 minus square root of D. So this is the settling time expression. Is this clear? How we are getting the settling time? So once we get this, now I can calculate the undershoot. Undershoot is what? Delta V is Q into delta, delta V is Q equal to CV, right? So delta Q, which is this charge corresponding to the undershoot. So I can say my Q1 is equal to C into delta V. So I can do that. So now for calculating the undershoot, I can get Q1 equals to C into delta V. And you know Q1 is how much? Q1 is delta I naught square by 2 into M1, right? So my Q is delta I naught square by 2 into M1. And we have just calculated M1. So let us substitute it. So we'll get delta I naught square into L by 2 into V naught into D by 1 minus B. And if we bring C this side, I can get delta V undershoot. So delta V undershoot is nothing but L into delta I naught square by 2 V naught C into D by 1 minus B. So is this clear?
Yes, sir. Sir, one doubt. This
Yes.
capital D is actually a steady state duty ratio, right?
Yes.
But we are
Steady state
using it in a very small transient time. This T1, T2, these are actually, is it duty ratio will be varying during that time, right?
Yes. So actually another assumption, very good. So another assumption we are making is we are considering all ideal. So the duty ratio ideally remains same. So thank you for pointing this out. I have missed this point. So we are considering ideal converter. We are kind of neglecting the parasitic, because if we consider parasitic, then slope M1 is not V in minus V0 by L. It will be V in minus V0 minus IL into the parasitic resistance by L. So we are kind of considering ideal, uh, converter. So the duty ratio is same before and after the load trend, because there is no drop. Is that clear?
Yes, sir.
Or we can actually leave in terms of M1 and M2, so that we are not converting into duty ratio. Then we know that from calculating M1 and M2, we know that it is V output by V input, which is basically not exactly duty ratio, but a certain gain. Then it's like a fixed number rather than writing in terms of duty ratio. It is just V naught by V, which is always fixed irrespective of the load triangle. So we can say in that sense also, but here basically we have considered ideal converter. Okay, so if things are clear, I have one problem for you. The problem is consider a buck converter with the following specifications under time optimal control. So I have given V in, V naught, inductance, capacitance, and switching frequency. So for a load transient from 1 ampere to 30 amperes, what is the value of peak current and what is the settling time? So in this case, what is delta I naught in this question? What is delta I naught?
29 ampere.
Very good, 29 ampere. So now I am asking what is the value of peak current as well as what is the settling time. So let me just copy paste the results. So I might as well ask what is the undershoot. So that also let us do. So you please calculate. In the meantime, I'll add one more part. Okay, so what is the value of peak current and what is the settling time and what is the voltage undershoot? So this will be the last problem of today's session. And using the results that we have obtained while deriving, now we are going to calculate. So Riddhi is saying 9.17 is the peak current. Okay, I'll wait for others, and once they get, I'll start some. I value. Yes, Riddhi is saying I value is peak is I naught into root D. She's getting 29. Sorry, not 29. How much? L value not seen. Okay, sorry. Okay, so let me calculate. I hope others are also calculating. So I'll get IP is 29 into square root of 1 by 10. So I'll get IP is nothing but 29 by root 10. 29 by root 10, which is 9.17. Very good. So it is coming 9.17 amperes. Now let us calculate the settling time. So TS is inductance. How much did I ask? 150 nanohenry. So 150 into 10 to the power minus 9 into delta I naught is 29 by V naught is 1.2 into so I can the duty ratio is 1 by root 10, right? So I'll get 1 by square root of 10 minus 1 if I simplify. So I think Riddhi is saying 1.6 milli. Let me calculate. So it is 150 into 10 to the power minus 9 into 29 by 1.2 into root 10 minus 1. So it is coming 1.6 micro, right? 1.6 micro. Not really, 1.6 into 10 to the power minus 6. So I'm getting my settling down is 1.6 microseconds. Yes, 1.6 micro. Okay. Now, if we do delta V undershoot, then it is L into delta I naught square by 2 into delta 2 into V naught. V naught is 1.2. See how much did I give? 1 millifarad, right? 1 millifarad, 1 millifarad, which is 10 to the power minus 3 into d by 1 minus d. So it is 1 by 10 by 1 by 10 minus 1. I will get 1 by 10 minus 1. So if we calculate this, it will become 150 into 10 to the power minus 9 into 29 to 29 square by 2 into 1.2 into 10 to the power minus 3 into 9. So I'm getting 5.8 into 10 to the power minus 3. I'm getting now delta V undershoot is 5.8 millivolt. Riddhi, is this what you are getting? Can you confirm? I'm getting 5.8 millivolt.
Yes, sir. 5.84 millivolt.
Okay, good. So this is like the final problem for today's session. Let me just quickly summarize. So we have started with the summary of previous weeks, where I have highlighted that we have learned about working of the switch mode power converters and then their design aspects as well as steady state analysis. And we have also studied about different control architectures like voltage mode control, current mode control. And we have also learned about the implementation using MATLAB. And then we have learned about the modeling, both DC as well as AC analysis using circuit averaging, state space averaging, and average switch model. And then we have also learned the analysis of how to get the small signal model and how to get the small signal transfer functions. And then we have seen that there is some accuracy issue with that. So we have also learned about more accurate model. And then using the small signal models, we have designed the controllers for both voltage mode control as well as current mode control. But we have seen that there is bandwidth limitations, which is limited to switching frequency by 10. And then the question that will arise is, can we further improve the response? Yes, we can use large signal model, which is again non-linear because of the switching action. So we have to learn how to deal with these nonlinear systems and how to visualize or how to realize. So we have learned about the trajectory where we discussed about the phase portrait as well as equilibrium points and their stability by using the eigenvalues as eigenvectors in the last week. So this week we have learned about the sliding mode control as well as time optimal control, which are both based on the trajectory based, where the trajectory concept was discussed in the week 9. So we have started with the sliding mode control where there will be a switching surface, and then we have considered a second order system and how the trajectory is moving across the sliding surface. We have seen that it will have infinite switching frequency, which is practically not possible. So we have to consider a practical implementation where there will be a finite switching frequency. So we have considered a hysteresis band, and we have seen how the trajectory is moving. And according to the controller, we have seen when it is coming below sigma 2, it is turning on. If it is going above sigma 1, then it is turning off. So we have also correlated with the hysteresis current mode control, where it has peak and valley current reference, and inductor current it hits peak and valley, and then accordingly the gate pulse is coming. Here instead of current, we have trajectory. Instead of the current reference, we have the surfaces, and it is not horizontal. It can be at an angle. Here we have considered negative slope. Then we have discussed about boundary points. There are 3 different boundary points, and we have seen their refractive point, as well as a reflective point, and we have seen how their trajectory looks like. And we have seen shattering happens in a reflective point because of the infinite switching frequency. And then one topic that I could not cover is the reaching condition because time will not be sufficient. So the reaching condition is sigma into sigma dot is less than 0. So for this, kindly refers to Sir's lecture. And then we have solved another problem where we have seen that the number of switching surfaces is equal to number of inputs, and depending upon the order of the system, we'll get the switching surface. If it is second order, we'll get a straight line. If it is third order, we'll get a plane. If it is fourth order, then we'll get a 3D surface. So overall, just to summarize, the dimension of the sigma will be 1 dimension lesser compared to the system. Then we have solved another problem where we have found the equilibrium points. As the input is switching between 8 and -8, we'll get 2 equilibrium points, and then we have seen what is the range of C for which the sliding surface is stable. So we know that when it is sliding on the sliding surface, it can come towards the equilibrium point or it can go away from the equilibrium point. So now we have the dynamics satisfy both the system dynamics as well as the surface dynamics. So using that, we got the expression, and we have seen if C1 is positive, X1 will diminish. So it is stable. Then we have discussed about the other aspect, which is the time optimal control, where we have single switching. Within single switching, we are moving from one operating point to another operating point. Here also we have sigma, so it will hit sigma and then it will reach the new operating point. So now we need to find out the different parameters during this tangent. So we have come back to time domain where we have this time optimal control, and whenever there is tangent, inductor current supply the delta I naught. So there is a delta I naught dip, and then it will undergo this on and off modes to reach the new operating point, and we have considered T1, T2, T3, and this is the delta we understood. So now using the charge balance, first of all, we have considered 2 assumptions. One is ripple is small, so we have neglected the ripple, and also ideal converter. So slopes remain same, and V naught is also same. Now T1 is delta I naught by M1, T2 is I peak by M1, and T3 is I peak by M2. Now applying charge balance, we have gotten I peak expression, and for a buck converter, I peak is I naught into square root of D. Then we have calculated the settling time, and we have done the simplification to get the settling time. Similarly, we have gotten the delta V understood. Now we have solved one problem where a buck converter is given with input voltage, output voltage, and inductance and capacitance values given, and switching frequency is also given. Although it is not related to the redundant for this problem. there is a load transient from 1 ampere to 30 ampere, and I have asked what is the peak current settling time as well as voltage understood, and from the expressions that we have obtained, like the final results we have calculated, and then we have compared. So this is the overall summary of this week. Next week there will not be any session because I will be out of station. So the next session will be next to next week. If I'm not wrong, it will be 6th October, 5th or 6th October, Monday, 6 to 8 p.m. with week 11. So if you don't have any queries, I will end this session here. If you have any queries, you can ask me. Okay. If you don't have any queries, then we can wind this session here. I wish you all the best for both week 9 as well as week 10. Week 9 I have taken last week Saturday, 4 to 6 p.m. and I have already uploaded the video. I'll try to upload this video by tonight. So please go through these videos. If you have any queries, you can ask me. And these are the week 10 might look little bit complicated because of all the trajectories, but it is simple. Kindly go to Sir's lecture. Then you can also refer to my problem solving session, then it will be more beneficial. And then you can be prepared for both week 9 as well as week 10. So we are approaching towards the end of this course. So please be like confident about all the topics so that it will also boost your confidence from the final exam. Both weeks are simple, week 9 especially, and week 10 is also simple. It might look a little bit complicated because of all the math and trajectories, but it is simple once you understand the concept. So kindly go through Sir's lecture and then we'll do this. So with this, I'll end this session here. Thank you for joining and thank you for making it interactive. See you again next week on Monday, 6 p.m. to 8 p.m. So with that, I'll end this session here. And I wish you all the best for both week 9 and week 10. And yeah, see you in the next section. Good night. Arun, are you trying to say something?
Thank you.
Thank you.
Thank you.
Thank you.
No.
Thank you, sir.
Thank you.